cylinders that are equipped with a piston, and when the combustion reaction occurs, the work is done by the system against the surroundings. And you can see in this little picture over here, we've got a couple of cylinders. We've got our initial state and our final state. In our initial state, we've got the volume down here, the volume inside that cylinder. And after the combustion reaction, we see that the piston has been pushed up. And so the height has changed. That's delta H, right? Or the distance. So we defined work in the last class to be the force across some distance, right? So capital F, so up here, capital F, we get our force across some distance, D. In this picture down here, that D is going to be the height if we're talking about a cylinder. And then the volume, we talked about the last class, is just the length times the width times the height, right? Or the area times the distance, or in other words, the area times the height. Well, if you're comparing your initial conditions to your final conditions, you have a combustion reaction that causes work to be done against the surroundings by the system. So the system is in here, inside the cylinder. When the combustion reaction occurs, you're going to increase the volume of the cylinder, so you're increasing the distance, and so therefore the change in the volume of the entire cylinder, the area, so the cross-sectional area is not going to change, right, of your cylinder, but the height will. And so we're going to take that area and we're going to multiply it by the change in the height. We get our change in volume. So let's just quickly redefine work and take a look, number one, at the fact that we've got an exothermic process here. If you want to look at the diagram, as the gas expands, that volume is going to increase against the surroundings. So the work is going to be done by the system onto the surroundings. Imagine you are at the gym, right? You're the system. You're expending energy. So work is being done by you onto your surroundings. So if you're that cylinder, and inside there's a reaction happening, it's exothermic, work is being done by the system against the surroundings, pushing the piston up, increasing the height. So when we redefine the work, let's just write out everything that we know. What do we know? Well, we know that work is a force across some distance. We also know that force can be defined as the pressure times that cross-sectional area, because we know that pressure is just force per unit area, right? So then if we want, we can substitute, and we did this in the last class, so this is kind of a bit of a review, but we can substitute in for the force in the work equation. So the work is going to be equal to the pressure times that cross-sectional area times the distance. And if we say, let this be the height, right? So this is going to be the height so the change in the height of the piston in our little cylinder up there as the reaction occurs. So in other words, then, we can rewrite this as the work is going to be equal to the pressure times that area, that cross-sectional area, times delta H. And this right here is that height. But we also know that the volume is equal to the length times the width times the height. This right here is the area, that cross-sectional area, and this right here is the height. that's going to change, right? In our piston, the cross-sectional area stays the same. The height is the thing that's going to change. So in other words, the change in volume is going to be equal to the area times delta H. So that means we can substitute into our work equation. So down here, work is going to be equal to what? If area times the change in height is equal to volume, then pressure times the change in volume is going to be equal to the work. And for an exothermic process, like the combustion reaction, work is being done by the system onto the surroundings. So therefore, we say, if the work is being done by the system, we have negative work, right? We're putting out work. It's going to be equal to the pressure times the change in the volume. Or more conveniently, work is going to be equal to negative P delta V for an exothermic process. So let's see how we can sort of put this to use. Let's quantify some energy through work and heat. So this is when you have both components to consider. So we have an example here. When fuel is burned in a cylinder equipped with a piston, so just like that picture that we saw above, the volume of the gas is going to expand, right, inside your cylinder from 0.244 liters to 1.44 liters. And it's going to be against an external pressure of 0.976 atmospheres. In addition to that, 878 joules of energy is emitted. They're asking you, what is the change in energy for the entire process? The change in energy for the entire process. So first of all, we have to notice a couple of things here. First of all, we notice that the word emitted is being used. What does that mean for us? It means that the heat is being given off. So negative Q. What else do we notice? We are doing work against an external pressure, right? So that work being done against an external pressure for us means negative P delta V. Work is being done by the system against the surroundings or onto the surroundings. So then let's define what we know to be the change in energy for the process. We know that our change in energy is going to be equal to the work plus the heat. We also now know that our work is going to be negative P delta V. So it's going to be equal to negative P delta V, because we just read that work was being done against the surroundings, plus heat is being emitted, so negative Q. Meaning we're going to use the values that they give us, and we're going to put those signs in ourselves. So the change in energy for the whole process is going to be equal to negative P delta V plus negative Q, because this is an exothermic process. So let's fill these data in. So over here, I'm just going to write the change in energy for the entire process is going to be equal to, so negative P delta V. I'll put the negative on the outside and put my P delta V inside. My P, the pressure I'm given, the external pressure, is 0.976 atmospheres times the change in volume. So that's going to be my final volume minus my initial volume. I just want to find the difference between those two values. So 1.44 liters is my final volume, right? The gas, it says the volume of the gas expands from 0.244 liters to 1.44 liters. So this is going to be my final volume minus my initial volume. So I get my change in volume. And then I'm going to add to this my heat component. And I see that this is exothermic. They tell me that 878 joules of energy is emitted. That means negative 878. We report these as positive values, right? we read the question, we see this energy is released, right? So it's given off. We're doing this from the perspective of the system. So let's put this together. We get essentially negative 1.16, and I'm going to carry an extra sig fig here. And this will be liter atmospheres minus 878 joules. But we have mixed units. Do you see that? Liter atmospheres and joules, not working out. We have another conversion factor that we can use. So down here, I'm going to, or over here actually, let me do it off to the side, convert our liter atmospheres into joules so we can have like units. So over here, I'm going to write negative 1.167, carrying the 7, liter atmospheres, because I know that 101.3 joules per liter atmosphere, 101.3 joules are in 1 liter atmosphere. And then to that, I'm going to add my negative 878 joules. Or from that, I'm going to subtract 878 joules, however you want to look at it. So these units are going to divide to 1, in other words, cancel out. And the change in energy for the system is going to be negative 996 joules. And that's going to be for the whole process. The other thing I notice here, though, is when I'm defining the change in energy for the process, I see that it is the sum of the work and the heat. But what is the heat? The heat is just a form of kinetic energy, right? Where does that energy come from? It can't come from nowhere, right? So we have a new value, a new concept here to talk about, and that's going to be the enthalpy. The enthalpy for the reaction, and for enthalpy, this is going to be a new symbol here, capital H. This will end up being the sum of all of the internal energies in the system, so potential and kinetic energy. And that's going to be a big deal for us, the potential energy, the energy of composition, remember? And all of the products of its pressure volume work. So for us, we want to write down, what did they just say to us? Well, H for the enthalpy, otherwise known, you guys, as the heat of the reaction. Let me show you why. Capital H is going to be the sum of all of the internal energies. So let's call this capital E. And what are those? The work plus the heat plus the pressure volume component. What is that for an exothermic process? Negative work. So the enthalpy for this particular process, either at constant pressure or for an exothermic process, right? We've got the enthalpy for the reaction, or the heat of the reaction, is going to be equal to the sum of all of the energies, work plus heat, minus work. So in other words, the change in the enthalpy for the entire reaction is going to be equal to the change in the heat of the reaction. And we can measure the heat by measuring the temperature. So this becomes pretty convenient. At constant pressure, our work component is going to go away, and we end up with the change in enthalpy for the reaction is equal to the change in the heat for the reaction, which is measurable for us. So I have a little example here. Remember in the, oh God, I can't even remember what chapter it was. It was probably like chapter 2 when we were talking about atomic theory. We were talking about bond energies, right? And so we talked about how, you know, if you're comparing, say, like a carbon-carbon single bond, a carbon-carbon double bond, a carbon-carbon triple bond, how the energy of those bonds is not the same. So here I've got nitrogen gas. And the physical state for these is going to be a big deal for us. We're measuring these bond energies. In order to break the nitrogen-nitrogen triple bond in the gas phase, we need to supply a certain amount of energy. How much energy? We have to supply at least the amount of energy that's holding that molecule together, right, in that triple bond. So we need to supply at least the bond energy of the nitrogen-nitrogen triple bond. In other words, we have to put in positive, in this case, 946 kilojoules of energy for every mole, right, of nitrogen, molecular nitrogen in the gas phase. So the flip side of this, though, is when we make the bond. So if I take 2 moles of nitrogen atoms in the gas phase and I allow them to come together and react and form the nitrogen-nitrogen triple bond in the gas phase, I'm going to release 946 kilojoules of energy per mole of reaction, okay? So if it takes 946 kilojoules of energy to break the nitrogen-nitrogen triple bond, that means when I form the nitrogen-nitrogen triple bond, 946 kilojoules of energy per mole of reaction are released. So in other words, all bond breaking processes require energy. I mean, it just kind of makes sense, right? If you want to bust up a bond, you got to put in some energy, right? Some heat, some light, whatever. All bond making processes are exothermic. So heat is emitted, thermal energy is emitted every time a bond is formed. Every time you want to break a bond, you have to put in energy. So this is going to be important to us as we move through the rest of this chapter. It's not always super convenient to simply just talk about the enthalpy of, say, the reactants or the enthalpy of the products. Very often we want to know how much energy can I get out of this reaction. Like if you have a hot pack, for example. So I'm going to crack a hot pack and I'm going to allow some powder, some salt to dissolve in water. And for a hot pack, we have an exothermic process. I want to know how hot a hot pack is going to get. Like how much energy can I expect to get out? Or for an ice pack, I want to know how much energy is going to be taken into the system from the surroundings. If energy is being taken into the system from the surroundings, then the outside of the reaction vessel is going to get cold, so an ice pack. But how cold is it going to get, right? So in order to calculate the change in the heat for the reaction or the change in the enthalpy for the reaction, so here, the change in the enthalpy for the reaction, I need to know what the sum of all of the enthalpies involved in the entire process is. And by that I mean I need to sum up all of the enthalpies of the products. So the change in enthalpy for all of the products, meaning you made a whole pile of new bonds, how much energy or how much heat was actually given off when you did that. So we're going to sum them up. That's what that big symbol there means. And from that, we're going to subtract all of the energy necessary to break up the reactant bonds. So the difference in energy between the amount of heat that is given off by the products and the amount of energy that was necessary to break up the reactant bonds so that they could form product, right, is the overall change in the heat of the entire reaction. So again, we're talking about bond energies. The overall heat of the reaction at constant pressure is simply going to be the change, right, or the change in the enthalpy for the entire reaction is going to equal the change in the energy for the entire process. So let's talk just a little bit about units for enthalpy of a reaction. We do our reactions on a per mole basis, and the energy is measured either in kilocalories or kilojoules. So typically for enthalpy, we'll see something like kilojoules, right? Nutritional calories, kilocalories, right? Very often are used when we're talking about the fuel value. So in other words, the energy per gram of a food item. So those are usually the units that we're going to see. And it'll be on a per mole basis, meaning if I've got the overall change in enthalpy for a process, and I'm talking about 1 mole of reaction, then I'm talking like, for example, the formation of the nitrogen-nitrogen triple bond from 2 moles of nitrogen atoms would be, because it's exothermic, negative 946 kilojoules of energy per mole of reaction, right, is given off. So I kind of want to take just a little bit of time to talk about the difference between some of these values you're going to see in your book versus some values you might run into elsewhere. There's two different ways that we can look at this. Your book uses heats of formation. So a heat of formation, we're talking in standard state. So we're talking about the standard state of a particular item. Like, for example, molecular oxygen. The standard state for molecular oxygen in the gas phase is zero kilojoules per mole. So meaning, now it doesn't tell you anything about the bond energy. The oxygen-oxygen double bond has a bond energy associated with it, but the heat of formation is talking about these particular species in their standard state. And really kind of what they're saying here is, well, let's imagine that oxygen, molecular oxygen, exists as O2 in the gas phase under standard conditions. And so, therefore, there is no heat of formation because that's just how it is, O2 in the gas phase, right? So zero, but it doesn't really give you any information about the energy of the bond. There's another way of actually looking at this and saying, you know, if I take 2 moles of oxygen atoms in the gas phase and allow them to come together and form molecular oxygen, O2, in the gas phase, we can measure the amount of energy or the heat that's put out by that reaction. There actually is a value, negative 498.340 kilojoules per mole of reaction. Your book uses heats of formation, so I will too. And the math that we're going to do with these data is all the same, but the heat of formation completely disregards the intermolecular forces. So for example, water in the liquid phase versus water in the gas phase. The intermolecular forces are all the same. They're just a little bit less significant in the gas phase. So in other words, the heat or the enthalpy, I should say, of atom combination for water in the liquid phase is going to be different than the heat of atom combination for water in the gas phase because it takes into account those intermolecular forces. So I'm going to use heats of formation because that's what your book uses, and we're going to go through these calculations using heats of formation. So I'm going to use the data on the left side of that table that I gave up above there. And so we have just a simple combustion reaction. Here we have 1 mole, so I've balanced this equation already. 1 mole of methane gas is going to react in the presence of oxygen gas, 2 moles of oxygen gas, right? In a combustion reaction that produces 1 mole of carbon dioxide in the gas phase and 2 moles of water in the liquid phase. So I wrote down liquid phase there and I got the data for the water in the liquid phase. You can write water in the gas phase and there's nothing wrong with that. The thermodynamic data will be different. So the heat of formation of gaseous water is not negative 285.830. It'll be something different. So you have to make sure that you're looking at the right physical state when you find these data in a table. The first thing that I'm going to want to do is I'm going to just itemize everything that I know. I see that my reactants are written over on the left, and I see that my products are written over there on the right. And so what I'm going to do then is I'm going to put the change or the enthalpy, so over here, let me do this in a different color so you can actually see what's going on. I'll do it in red. The enthalpy of formation under standard conditions in kilojoules per mole for all of the players in this reaction. So our reactants over here are methane, and we see from the table negative 74.81. So my unit's over here on the left, so I don't have to keep writing them down every time. I see that I've got a 0 for oxygen because under standard conditions, molecular oxygen, O2, is in the gas phase. So we've got a 0 for the heat of formation for that. For carbon dioxide, we see negative 393.509. And for water in the liquid phase, we see negative 285.830. It's important to see that these are all per mole. Our balanced equation, not everything is just one single mole, right? So let's do this out down here. The change in enthalpy under standard conditions for the entire reaction is going to be the sum of all the enthalpies of my products minus the sum of all of my enthalpies of my reactants or reagents. So I can go ahead and write this down over here. So this will be equal to, I like to separate these. I use big brackets to keep them apart from each other, and you'll see why in a second. That little negative sign there is going to get lost in the sauce if we don't separate these with some brackets. And so you got to be careful. The next thing you have to worry about, aside from the sign, right, is that you are starting with your products. So it's a little weird because we're going to take the difference between the enthalpy of the products and the enthalpy of the reactants, but in the balanced chemical equation, the products are on the right. You look at that equation, the expression that we just wrote, it's over on the left. You just got to be mindful not to use the wrong numbers in the wrong spot. So you'll have to stop yourself and say, where are the products? Okay, they're over there on the right. What else do I notice? I notice that I've got 1 mole. This is where you have to look at your balanced chemical equation. 1 mole of carbon dioxide. And you write that down because the value that you're given for the heat of formation of the carbon dioxide in the gas phase is negative 393.509, and that's kilojoules per mole. So you need to write down how many moles you have in your balanced equation. The sum of all of my products, enthalpies, right? So I put a plus sign there, and now I have to take care of the water. I see 2 moles of water. The value that I'm given for the enthalpy of the water in the liquid phase is negative 285.830 kilojoules per mole. But I have 2 moles in my balanced equation, right? And that's the end of my products. I'm going to subtract. That's why I like to use the brackets, so I don't lose that minus sign. I've got 1 mole of methane, and the enthalpy associated with that formation. Notice how we are subtracting our products because we're not forming methane, we're busting it up, right? If you want to sum everything up, right, and say that the enthalpy for the entire reaction is the products plus the reactants, you have to be mindful to switch the sign on your reactants yourself, because all of your heats of formation, if they're not 0, are going to be negative values, because the heat of formation, all bond making processes are exothermic. All of your values for your delta H are going to be less than 0, right? So if you're going to sum up the products and the reactants, then you're going to have to be mindful of changing those signs yourself. Or you can just say, let's find the difference. And if I keep my reactants separate from my products in their own bracket and I subtract them, right, then all those negatives are going to become a positive, just algebraically. I'm going to add up. I got 2 moles there of oxygen. If you look at your balanced equation, so 2 moles of oxygen. And 0 kilojoules per mole, because they're saying the heat of formation of oxygen in the standard state, well, if that's how it exists in the standard state, then there was no heat of formation because it just existed that way. So they're totally disregarding the bond energy. But we're going to do the math the same way anyway. I've got the change in enthalpy for the entire reaction under standard conditions is going to be equal to the sum of all the changes in enthalpy for my products minus the sum of all the enthalpies of formation for my reactants. And I end up with an overall enthalpy of the reaction of negative 1.93. And this will just be kilojoules, not kilojoules per mole. Why is that? Because look what happened. All of my moles canceled out, or all of my moles divided to 1. So everything's in kilojoules. What happens though if you don't use 1 mole of methane? So we had this balanced equation, and that's fine, right? But what happens if you don't use a full mole of methane? What if I use, say, for example, 2.17 times 10 to the negative 3 moles of methane? Let's do this out. We still have to write our balanced chemical equation. So up here, I'll just squeeze this in. So methane in the gas phase, 2 moles of oxygen gas is going to give us 1 mole of CO2 gas. And if we're going to use those data, I'm going to keep the water in the liquid phase. And they want to know what the change in enthalpy for the reaction is going to be. So I have to take into consideration that I use less than 1 mole. And why do I have to do that? Because all those data were given as kilojoules per 1 mole. I don't have a whole mole of methane, do I? I have 2.17 times 10 to the negative 3rd moles of methane. That's going to affect the enthalpy for all of the other things involved in the reaction as well. So we're going to compare all of our mole ratios here. I've got negative 74.81 kilojoules of energy emitted per mole of the formation of methane. But if I only use 2.17 times 10 to the negative 3 moles of methane, then my new value is 0.162 kilojoules, because see how these go away, my moles of methane, when I use 0.00217 moles of methane gas. And now I have to figure out the amount of all of the other, or the enthalpy of all of the other species in the reaction. I'm going to start out with the amount of methane that they said we were using, because that's all the information that you have. And then I'm going to go back to the balanced equation, and I'm going to say, okay, I'm just going to go from left to right. I see that 2 moles of O2 are consumed when 1 mole of methane reacts with it. And then I look up at the table and I see that the heat of formation for oxygen in its standard state is 0 kilojoules per mole. So the moles of methane are going to go away, and then the moles of O2 are going to go away, and I'm left with just the enthalpy. So I have my energy unit here, and that'll be 0 kilojoules. If I start out with 2.17 times 10 to the negative 3 moles of methane, and I look at the balanced equation, I see that 1 mole of carbon dioxide is formed when 1 mole of methane is consumed. And then I have a value, right, for the production or the formation of carbon dioxide gas per 1 mole is negative 393.509 kilojoules. And this would be per 1 mole. But I'm not using 1 mole, am I? I'm using 2.17 times 10 to the negative 3 moles, because we have a 1-to-1 mole ratio. And these moles will cancel. So I got what? Let's see. Negative 0.8539. I'm going to carry that. Kilojoules. And the last one that I have is for water. So 2.17 times 10 to the negative 3 moles of methane. They're telling us how much of this reactant we start with. So we have to figure out, how much of the product we're going to make. We see that 2 moles of water are produced when 1 mole of methane is consumed. We have the thermodynamic data for the production of 1 mole of water in the liquid phase, and that's negative 285.830 kilojoules of energy for every 1 mole of water in the liquid phase. So here, My moles of methane are going to cancel out. The moles of water are going to go away, and I'm left with just the energy associated with that process. Negative 1.24 kilojoules of energy. So if we use less than 1 mole, right, of methane, then we're going to produce less energy for the water. So we can put this all together, same way we did before. The change in the enthalpy for the reaction under standard conditions is going to be, we can bring out our little brackets again if you like, keep track of everything. So negative, let's see, what do we have for our products? What do we have? Carbon dioxide and water, so negative 0.8539, carrying that sig fig. And that's kilojoules of energy, right? And then we're going to add to this the negative 1.24 kilojoules of energy associated with the formation of the water. To get the change overall for the enthalpy in the entire reaction, we have to subtract the amount of energy that was necessary to break up the product or the reactants, right? So here's where I get a little irritated. Not irritated, but just kind of like, come on, seriously? Like, you think that it's not going to take any energy to bust up oxygen? Well, if we're using heats of formation, they are telling you that under standard conditions, there is no energy associated with that particular species because it's in its standard state. But in the reality is you have to break up O2 in order for, the oxygen to react. But that's okay. The math is done the exact same way. You would still be doing the same calculation, just using different values. So what do we have here? For the methane, I've got negative 0.162 kilojoules. And I'm going to add to that nothing because they're saying that the heat of formation for molecular oxygen under standard conditions is 0. So the overall change in the enthalpy for this reaction, if we're using less than 1 mole of our starting material, is going to be negative 1.93 kilojoules. Wait, that looks awfully familiar. Did I accidentally write down? I did. I'm sorry. Let's roll back up here and erase this. I was looking at the wrong thing. This up here is actually much bigger than that. Let me add this up. Negative 890.36 kilojoules. That makes a lot more sense now. Okay. Sorry about that. But notice how we have less energy associated with the overall reaction when we use less moles of our starting material. That just makes sense, right? Because this is on a per mole basis. Okay, so let's put this into something that we might care a little bit more about. Not too many people are worried about, the energy associated with the combustion of 2.17 times 10 to the negative 3 moles of methane, but you might go camping, right? So let's check this out. So you're camping. I made this problem up. I think it might be kind of fun, and it's something that allows us to actually use the heat of the reaction. So often you're actually given the change in the enthalpy for the reaction, and you're trying to make some practical use out of it. So say you're camping with your friends over Thanksgiving, and you all decide to make a feast. So the fire pit's being used for the main course. So you break out your little camping stove to cook a dessert. You're making an apple crisp. Your stove comes equipped with 100.0 grams of butane, right, that little tank, for fuel. And if you let that gas undergo combustion reaction, right, you're going to produce heat. So that heat of the reaction is going to be the heat necessary to cook your dessert. So I'm giving you here the overall change in enthalpy, or the heat of the reaction. This is going to be negative 2,877.5 kilojoules per mole. So in other words, 2,877.5 kilojoules per mole of reaction are going to be available to you, because that's the heat that's put out by the reaction. That's why that's a negative, right? It's an exothermic process. But you are not the system, right? your crisp is the surroundings. So it's a positive 2,877. See how you got to look at that a little differently? Okay, the heat put out by the system, in other words, the heat put out by the combustion of that gas is going to be the heat that is absorbed by the crisp. Okay, so let's just write this stuff down. We're going to put this into terms that will be important to us to figure out how much, what are they asking anyways? If the apple crisp must absorb 2.4 times 10 to the third kilojoules per kilogram of heat to fully cook, so that's per kilogram of crisp, right? So that thing has to absorb 2,400 kilojoules of energy per kilogram of apple crisp to fully cook. How many pounds of apple crisp can you make if you're okay with blowing through your whole tank? Okay, so we're going to write down a balanced chemical equation for the combustion of butane. So we've got butane, and that'll be gas. We have to allow this to react with some oxygen, gas, and we're going to make CO2, and in your fire, we'll probably have this in the gas phase. And so the overall enthalpy of this reaction that I got is that value right there. And that is based on water in the gas phase. This is not balanced, by the way, so I'm going to go ahead and balance this. Okay. That will matter to us when we go to do this calculation because we need to turn those 100 grams of butane into moles because I have 1 mole of reaction, right? And my value here for the combustion of this reaction, the change in enthalpy for this reaction is actually per mole. See over here? So I need to know how many moles of butane are associated with a mole of the reaction. So balancing that equation was important. So I know the mass of the butane I started with. I'm going to start with that information. 100 grams of butane. But means 4, by the way. That's how I know there's 4 carbons in this. I would give this value, like I would give you the molecular formula. I'm just giving you a little bit of information so that you know how I knew that that was C4H10. I also know that I can calculate the molecular weight of butane. So 1 mole of C4H10 has a mass of 58.123 grams. Now I know in 100 grams of butane how many moles of butane I have. So let me write that down. This is going to give me, so I'm converting here, mass of the butane to moles so that I can use my balanced equation to see how many moles of butane I'm going to have per 1 mole of reaction. Because if I have 100 grams of butane, right, I'm going to have a little bit more than a mole. So I know that my balanced equation says that 1 mole of that reaction is going to require 2 moles of butane. And the reason I care about that is because the enthalpy of the reaction that I'm given is per mole of reaction. So see that negative 2,877.5 kilojoules, that's per mole. The other thing we have to be mindful of is that that's an exothermic process, but our apple crisp is the surroundings, not the system. So that is going to take on positive 2877.5 kilojoules of heat per mole of reaction. So here, this is my mole ratio of butane to reaction. And here is the heat put out by the reaction and absorbed by the food. Okay. Now what am I going to do with this? Because now I'm left with kilojoules. Well, they want to know if, to fully cook my apple crisp, I require 2.4 times 10 to the third kilojoules, right? Or 2.4 megajoules of energy. I can put down here 2.4 times 10 to the third kilojoules of energy are required to cook 1 kilogram of my crisp. Because we started this whole process out with the 100 grams of butane, we are going to blow through the whole tank and see how much crisp we can make. So here is the heat required to cook the food. And then the last thing we have to do is just turn our kilograms into pounds, right? I know that a pound is 454 grams, so that's 0.454 kilograms. And so down here I can write, I'm going to convert kilograms to pounds, because that's the unit they asked for. So if I do this out with, it looks like 2 sig figs, I'm limited by the heat necessary to cook the food, and I get 2.3 pounds of crisp before I kill off my tank.